Hi, this is Stats. We're going to do section 2.2. This video unfortunately comes in 4 parts because this is a really big section. So just watch them at your leisure. You pretty much have the weekend. I am really tired right now. It is about 6 o'clock in the evening. So if I say something that sounds really silly, then you'll just have to excuse me. Okay? Alright, so in this section we're going to do 2.2 density curves and normal distributions. All right, and then there's a couple of parts to it. So here's your objectives for the entire sections if you wanted to write them down. All right, in this one we're only going to do density curves and normal distributions. Actually, I shouldn't say that. We're going to do density curves, describing density curves, and then introduction to normal distributions before we branch into deeper things. Okay. So, first one. In Chapter 1, we developed a kit of graphical and numerical tools for describing distributions. Now we'll add one more step to the strategy, and this is exploring quantitative data. Always plot your data, make a graph, dot plot, stem plot, or a histogram. Something to look at, basically. Look at the overall pattern, shape, center, and spread. And then just a reminder, if you have, okay, I'm going to do this as a reminder, if you have a roughly symmetric graph, or whatever it is you're using to plot your data, you're going to use the mean and the standard deviation for roughly symmetric. If it's skewed, doesn't matter which skewed it is, right or left, you're going to use the median and the IQR to figure out your center and your spread, Okay, calculate numerical summary to briefly describe the center and the spread. Okay, so center, spread, depending on what your graph looks like. And then sometimes the overall pattern of a large number of values is so regular that we can describe it by a smooth curve. And this is going to be the main idea of today's section. Okay, if you have such an overall pattern, usually roughly symmetric is kind of what we're going for, but sometimes it tends to be a really nice pattern skewed, depends on which. We can describe it by a smooth curve, right? And the curve is what is in the next slide, which is called a density curve. Okay, is always on or above the horizontal axis. So this is your horizontal axis down here. So it's always going to be above the horizontal axis, and the area under the curve is going to be exactly equal to 1. I know this looks really weird. You're like, how in the world is this equal to 1? You have to remember that we're actually doing proportions or percentages. So usually when you have proportions or percentages, when you add them all up together, should always equal to 100% of your data. In this case, 100% of your data basically just means exactly that your area under the curve is exactly equal to 1. So this is my curve. I'm going to darken it in a little bit. Okay. The data is so nice that we can actually use a curve, okay, to describe the overall pattern of it. All right. A density curve describes the overall pattern of the distribution, the area under curve, and above any intervals. And above any intervals, the values on the horizontal is proportional to all of the observations that fall in that interval. So basically, you have to be all of your data points have to be underneath here. And if you add up all the probabilities of each of the data points, you should get 100% of your data. So your area under the curve, we're going to call that 1 because it's 100% of your data. Okay. So, the overall pattern of this histogram of the scores, here's a couple of scores on the Iowa test of basic skills, and then we're going to work with this problem in the next example in a second. Actually, not in this one, in the second video. We're going to talk about the Iowa test of basic skills data. So this was a bunch of this was a histogram, and then since the pattern is so nice for us, we basically can use a curve or density curve to simulate most of the data, right? Or we can describe it by a smooth curve. Okay, God, I'm like exhausted. I'm barely hanging on here. Are measures of center of spread applied to density of curves as well as to actual sets of observations? So distinguishing the mean and the median of the density curve. We've kind of gone over this before, but it just really trying to bring the point home. The median is the equal areas point, the point that divides the area under the curve in half. Okay, so before it was half of your data, but now it's dividing the area under the curve in half. All right, and then the mean of the density is the balance point. Okay, so basically which way it's going to fall. And then the median and the mean are the same for the symmetric density curve. They both lie at the center of the curve. So if it's skewed, right, we've talked about this before, the mean curve is pulled away from the median in the direction of the long tail. So this is just a re-verification of what I've explained to you guys before, but now we're talking about the areas under the curve instead of just the data points. So if you have a roughly symmetric data points, you can simulate it using a curve, or your density curve, and then your mean and your median are going to be right in the middle, balancing everything out. But if it's right skewed, okay, then your mean is going to get pulled towards the tail. Your median is still going to be in the middle. Your median divides this area, and this is the part that is a little bit different than what you've dealt with before. This part, so this area in orange, okay, is going to be as equal to this area in blue. Okay, so your median, smack dab in the middle, is going to be halfway. This is going to cut the area under the curve, even on this side and even on that side. Even though it doesn't look like it, the areas will be the same wherever your median is. And your mean gets pulled towards your tail. And it would be the same thing if you had a left skewed. It would just be, flipped. All right. We distinguish between the median, the standard deviation of the density curve, and the mean and the standard deviation computed from the actual observation. So a density curve is an idealized description of a distribution of data. The usual notation for the mean is mu, which is this one right here. And the standard deviation of a density curve is sigma. Sorry. For some reason, I thought that was rho, so I may have said rho in class. It's sigma for standard deviation and mu for mean. But I usually just use mean or x bar, one of the two. And then that's your description of density curves. There's not really that much to them. Normal distributions. Okay. Now, the reason we talk about density curves and then normal distributions is because in density curves, you can have roughly symmetric. You can have roughly symmetric. You can have right skewed, or you can have left skewed. So you can have all three of them, and then you can still talk about the mean and the median and things like that in a smooth curve, even though it's right skewed, left skewed, roughly symmetric. But what we're going to really get into is the normal distribution. So we really want to talk about more about the ones where they're roughly symmetric. And these ones we call our normal curves. So when they're roughly symmetric, those are the ones we really want to kind of discuss, that we're going to go more in depth about. So you can either be I shouldn't say squished, but you can have a lot of data, right? And so it's going to be a little bit more spread out, or you can have a smaller number of data all concentrated here. So we call these normal curves, which describe normal distribution. So all normal curves have the same shape. They're symmetric, single peak, bell-shaped. Bell from like this part right here. Any specific normal curve is completely described by giving its mean, mu, and its standard deviation, sigma. All right, next. So there's your mean, there's your standard deviation, there's your mean, there's your standard deviation. All right, so why do we want to know this? This is the slide of why we want to know this. A normal distribution is described by normal density curves. Any particular norm is completely specified by two numbers, its mean and the standard deviation. The mean is the center, right, of the normal curve. The standard deviation is the distance from the center to the change of curvature points on the other side. So basically how far away you are from the point of curvature. So point of curvature being you're changing your curve, at the top, which is basically where your mean is. We abbreviate the normal distribution mean mu, standard deviation as sigma, as normal. Okay, so I had to stop here for a second. So n means normal, mean, comma, standard deviation. So typically if I say, okay, well, I want you to, or I'm giving you a bunch of data, it's going to be in the normal curve, and I'm just making up something, right? Your mu is going to be, your mean is going to be 30, and a standard deviation of 5, all right? We're going to discuss this in the next couple of slides in the next video, how we're going to actually do calculations on this. So why are normal distributions important in statistics? They're good descriptions for the describers of real data. Okay, so if you have some data that looks, roughly symmetric, if you can create a bell shape, right, or a smooth curve, your density curve to model the data, it makes sense to do that because then you can get some numbers really fast, and you'll see why in just a second. Okay. And then normal distributions are good approximations of results of many kinds of chance outcomes. That's true. They're good approximations. They're not like super the best. No model is going to be super the best, but if you can get a good approximation, then why not use it? Okay. And many statistical inference procedures are based on normal distributions. If you're in AP Bio, if you're in AP Psychology, AP Physics, you want to figure out, what type of shape your data is, and then can you model it with a normal curve? That is the question. If you can, you're sitting pretty good, right? Okay, and that is it in this video. There's your introduction, and the next one's going to be a little longer, so just bear with me as we get through these.